right, good morning, guys. We're from Edwards Miller. We plan to give you a little more information today. So, my name is Antonio Alexander. I'm an employee of Edwards Miller.
Microphone, please.
Microphone. Can you hear me now?
Yeah.
Okay, sorry about that. My name is Antonio Alexander. I'm an employee of Edwards Miller. I'm a senior integration architect. Edwards Miller is a company that specializes in ruggedized embedded electronics and the medical device field, oil and gas, as well as medical device field and oil and gas. We also do control systems. I specialize in LabVIEW. I've been doing LabVIEW since 2012. I first started in automation. Now I started at Edwards Miller in 2015. I'm a graduate from the University of Houston in computer engineering technology.
So my career path has been pretty similar to Antonio's. I graduated from the University of Houston. I think he beat me by a semester. We both worked at automation together and moved over to Edwards Miller. So we've had several years of working together and working in a team environment. We found some pitfalls when working as a team on projects in LabVIEW, and so we're here to share some of those pitfalls and some workarounds that we've found best fit our scenarios. So the title of the project, or this presentation, is Efficient LabVIEW Projects, a team-based approach. So I want to start by mentioning Brooks' Law. Brooks' Law states that adding manpower to a late project makes it later. We look at this as you don't necessarily double your efficiency by adding another developer. You're not necessarily going to deliver a project twice as fast. Another way to look at it is 9 women can't make a baby in a month. So some of the reasons that we lose this efficiency is because we have increased communication complexity. We need to make sure that we're organizing all of our project resources and developers. We have source integration issues. We need to make sure that we aren't overriding each other's code changes. This involves good architecture on our part. And finally, more complex source control measures, and in that case, dealing with diffing and merging. So we'll go through these one by one.
All right. So again, one of the biggest issues of working in a team of developers in LabVIEW is that adding more people does not increase your efficiency. But we have devised some strategies to help you mitigate that loss of efficiency. Those strategies are selecting a workflow with requirements and roles and responsibilities, choosing a LabVIEW architecture that makes it easier to merge conflicts in source control, as well as developing a known project lifecycle. So all those involved in the project, including developers, project heads, and project stakeholders, have a clear idea of when the project beginning, middle, and end.
So starting with the workflows, there's two that are very common. I'm sure everyone in this room might know about them. The waterfall and the agile development cycles. Waterfall tends to be a top-down approach, implement the entire scope of your project in one go, where you start with the requirements, design your architecture, implement it, validate it, and then release it to the client and maybe have to maintain the software from then on. The other one is agile, which tends to be a more iterative workflow. You develop functional subsets, so you have a more limited scope than waterfall. However, you're still implementing the waterfall process, just on a much smaller scope of work.
So again, oftentimes agile and waterfall method are competing against each other. When they are in fact the exact same process, the only difference is the scope is different. Generally, the agile process will be on a functional scope of work, where it's a small subset of the entire project, while a waterfall, it shouldn't be the scope of the entire project. So both the waterfall and agile methods have different pros and cons in certain situations. For example, there are generally two types of projects. There are two types of projects where you have a project, which is has a very definite start and end. This is our goal. And you have a product which you have to maintain, generally going over multiple different versions, adding new features, and fixing bugs. So with that in mind, the agile method is much better at doing our product because you can go from start to having something functional and being able to bring to market much sooner with the agile method than the waterfall method. While the waterfall method in and of itself is very good for projects that have a fixed timeline. Project with a fixed timeline, you can use the waterfall method and generate requirements, and go through the entire steps to be able to finish the project in a known amount of time.
So both of these workflows that we've mentioned start with a requirements phase. Agile, you might revisit the requirements every iteration. Waterfall, you tend to want to get all of your requirements up front. Requirements are statements that define the needs of our project. We'd like to use requirements to help identify the scope of our project, which aids in architecting the software, as well as on the business side, allows us to monitor change management, which is very vital in a fixed bid type project. We recommend that you store your requirements in a single shared document. Ideally, put this on a network drive or a cloud-based storage solution. This ensures that all of your developers, your project managers, and the team as a whole has access to this document at all times, and also that they're all using the latest version, because nothing will kill your architecture quicker than different requirements being passed around. So we have two examples of requirements here. In green, we have a suggested good requirement. In this case, if pressure is greater than a user configurable limit, software will trigger safety interlocks. See the safety interlock section. We like this requirement because it's concise, it's specific, and it doesn't duplicate other requirements. So in this case, instead of mentioning all the safety interlocks that we're going to trigger, we define those in another section and just refer to it. In red, we have an example of a bad requirement. Software can control a pump manually and automatically. One, this is very vague. What does it actually mean to control a pump manually versus automatically? And two, it's a compound requirement. So it's really two requirements in one. Our software needs to be able to control this pump manually. It also needs to be able to control this pump automatically. When you combine requirements, it makes it harder to write validation test plans. So generally, you want to separate them. And the focus is all of your requirements should be capable of being validated. So for example, if I specify a requirement, the user interface should be user-friendly. User-friendliness is subjective. You can't possibly validate that in a test plan. So make sure all of your requirements can be validated and tested. Oh, and finally, get your clients to sign the requirements document and agree to it before you start development.
So again, keeping in mind that the focus of this is a team-based environment. Requirements can be used to drive development. Oftentimes you have multiple team members, and those team members need to have an idea of what it is they are responsible for. So requirements can be used to create tasks for different developers to perform and complete. On the validation, they allow a developer on their own to be able to start a task and complete a task using the validation test scenario. So the requirement, if pressure is greater than a user configurable limit, software will trigger interlocks, can be used to create two different tasks. One task would be to use a data acquisition device to acquire pressure, and the other would be to create source code that can trigger an interlock when that pressure has been reached.
So another part of defining our project workflow is also to define our project team. So this includes your software developers, and we like to break them down into three subcategories. Your developers, which are about CLAD, CLD proficiency, integrators that are a CLD, CLA type proficiency, and then we like to specify one certified architect to architect our software. We recommend only picking one architect. If you pick multiple, you end up with a too many cooks in the kitchen type scenario, and architecture can get messy. That isn't to say that your architects can't all contribute to the design of the architecture, but one person should be making the final decisions and implementing the architecture. Alongside your developers, you also have your business resources. It's your project managers. They're responsible for managing the workflow, making sure everyone is following the project lifecycle. And then you have your client managers who are responsible for handling the client relationship, communicating with the client, but also looking into the future and trying to determine what the client might need and trying to anticipate their needs. Finally, you have external resources. These could be resources belonging to your client or even another third party. Some of these resources are your client point of contact, the person who is responsible for handling all communications with your company. And we have subject matter experts. These are usually more knowledgeable in the problem that we're trying to solve with software. And then you'll have your test engineers. These are oftentimes the end users who are actually using your software, and a lot of times their feedback becomes the most important. Finally, you might have external software developers. It might not always be economically viable to hire full-time developers on staff. And so working with third-party resources can be even more tricky as they're not always physically present when interaction occurs.
All right, so along with those roles, you have responsibilities. So in a team environment, one of the easiest ways to do is to divide the work up and say, this is your responsibility, this is your responsibility. So the three roles we have defined are the developer, the integrator, and the architect. These are ideas and not necessarily attached to their actual function or their experience. You can have an architect or an architect doing developer roles and an integrator doing architect roles. So, in the image on your right, you have an idea of an architecture. Our general idea is that you have your modules, and your modules group similar code, and that you have integration code which connects your modules together to create the functionality you need between those modules. And you may have a user interface that will interact with those modules to get data or create functionality, use functionality. So a developer will implement user stories or implement certain specific tasks, very focused tasks within a module, while an integrator will integrate the functionality together. So there may be multiple modules that need to talk to each other, and that will be done by an integrator, while an architect will maintain the overall software direction and the architecture direction. So they make sure that everyone's work is going towards the same task as defined in the requirements.
So Antonio talked a little bit about where our developers line up within our architecture. So I want to talk a little bit about architectures. A good architecture should follow the principles of low coupling, high cohesion. A good architecture needs to be scalable. It's an absolute requirement. The scope will always change, and because of that, we should be able to easily add and remove features. So in the image on the left here, we have a diagram for kind of a high-level view of what our architectures tend to follow. So we might have separate modules, each encapsulating some kind of functionality from our requirements. We like to follow the principles of high cohesion, so each of these modules should be responsible for like tasks. So a module that's responsible for handling all of our logging, a module that might be responsible for doing our data acquisition, etc. And around each of these, well, actually, in terms of module functionality, this is where your developers tend to code. They're responsible for the nitty-gritty details within a module. And then we have our integrators who write the API, the application programming interface, that we use to provide inter-module communication. All of these modules are built up to support our user interface, to allow our users to interact with the underlying software. And the architect is responsible for designing the skeleton of this system. So one example of an architecture, and this is my preferred architecture, is the model view model approach. MVVM was designed by Windows to support the WPF and Silverlight environments. It defines three components. We have the model, which is our data structure for each of our modules. So every module will have a model. We have views, which are simply just user interfaces. And the view model, which acts as our liaison between our models and our views. The view model is responsible for notifying the views of updates to the data model. And the views notify the view model that the user would like to change our underlying data models. So I do have pictures. In the top right here, I have a cluster of log data. This is considered my model data, the underlying data structure that is specific to my logging module, in which I'm defining a path, a log name, and a log rate. When I go to build my view model, I take this model data and I encapsulate it into a data value reference, or DVR. And then alongside that, I like to generate a command event. This is how other modules can notify my logging module that I need to run commands like start, stop logging, change the log path or the log rate. And alongside that, I have several notifier events, usually for each variable in my model, to notify my views and my view model of updates to the data. This image here shows the block diagram of a view. Views are intended to be very dumb VIs. Their only responsibility is for binding to the data in my model via user events. So they will register for the user events from all of my individual modules and update their data accordingly. When the user interacts with my user interface, I use these command events for each of my modules to notify them of potential updates from the user. Architecting this approach allows me for great opportunities for code reuse. My modules do not care about the user interfaces that are in my software, because the user interfaces are binding to my modules and not the other way. Views can be swapped in and out of the project, as they are only responsible for binding to data and displaying it. And likewise, modules don't care about the other modules that exist unless I specifically force some communication between the two. So I can swap out modules and their view models from other projects and place them into newer projects. On the right, on the right is a typical main VI for an MVVM architecture. I start by initializing all of the view models for all of my modules in one go. I group them up into one cluster, and I pass this cluster through every VI in my software. This provides global access to all of my events for registration. So individual modules can register for their command events, as well as possibly notifier events from other modules. And all my views can bind to my notifier events in order to update and display data. After the program terminates, I simply release all of my references and deallocate my memory. Now, one issue with this is all of these references are global. So that means the data value references that store my model data for each of my modules is globally accessible. This can be very dangerous, but it's a development time error. So it usually involves, it can be resolved with just some training. So a simple rule of thumb, if I'm developing in, say, the logging module, I am not allowed to go and access the data value reference of my DAC module or any other module in the software. If you don't want to rely on training and you want to anticipate human error, you can encapsulate your model data inside classes or LV libs and provide some encapsulating functions. That's your get and set VIs. Another is all of these modules are inherently asynchronous. They're not intended to run in synchronous operation. So if you need some synchronous operation between two modules, it can get a bit tricky. It usually involves some kind of blocking parallel or inter-process communication, such as queues and notifiers. I don't recommend it. I never intended modules to run in synchronous operation. You can get serial-based operation internal to a module, but ideally you don't want your modules depending on each other. This keeps them separated and allows for better reuse of code.
All right, so my architecture of choice, while following in theory John's, its implementation is different. It is a modified QMH, queued message handler. In this module, the goal was that like functionality and access to that functionality should be centrally located with an emphasis on code reuse. The general idea, these block diagrams are really bad. General idea is that within the main of the module main.vi, there are two queues, a command queue and a response queue. Functions or commands are received serially, in which the command is received, and once it's received, the functionality is accessed, and the result of that functionality is placed in the response queue. This allows multiple like functions to be placed in a central location to be accessed. When working with multiple developers, being able to give a developer all the tasks for a like functions and having it in one place makes it much easier to manage that code. Right. So there may be multiple modules with this functionality inside of it. The modules themselves will also have a status loop. In this loop, they will periodically publish information about the module, whether it's initialized or if you're acquiring data at a set rate, you can also publish that as well. It's accessed via a notifier, which can allow you one-to-many communication very easily. In the top right-hand corner is the inside of one of the process modules that contains that hidden functionality. This module was for a Rigol power supply, and the functionality being shown here is a serial command to set the current channel of the module itself. Each of the module functions has an API. This API is the only place where the queues and notifiers can be accessed. And within the API, you provide it with a command and any data associated with that function, and it's sent via the command queue. And then once that functionality is finished, it's output via the response queue, and the result is generally going to be success or failure, as well as any errors. For certain commands, it may also provide data, in which the different API can be configured to output that data as well. Again, keep in mind that there is a VI for every single function. So there's the API is contained within a single sub-VI that can be used wherever you want to. This atomic module architecture is very integration heavy, meaning that the use of all the functions takes more work than, for example, the NVVM, in which you can integrate into a user event structure. This is primarily for the ease of code reuse. Whenever you want to reuse a function within a module, you copy and paste the API, which is a single VI that allows you to access that functionality. This effectively encapsulates the functionality from external calling VIs and ensures that the function that allows you to access that functionality and the functionality itself are incredibly separate. This is very good for code reuse in the event that you want to add more functions or you want to prevent API breaking changes. Very commonly, if you add more functions, previous projects that use that module or that functionality will break. But by having the API separate from the actual functionality in here, we can make it much easier to add functionality, fix bugs, and not break the API for previously used projects. All right. So the block diagram here at the bottom. The block diagram here at the bottom is an example of how the atomic module architecture would be implemented in a main VI, in which we which we load the module, Then from loading the module, we initialize the module and run the UI. Right. So we load the module, we initialize the module here, and we load the UI. And then from there, all the functionality is accessed. Some of the challenges to this atomic module architecture is, again, like the NVVM, it's inherently asynchronous. All the functions will execute serially because of the command and response queues, as well as the difficulty in implementing synchronous functionality. An example I used this atomic module architecture for was a recipe machine. So generally in a recipe, you're going to execute a set number of tasks or steps in a very specific order. This architecture is very useful for that. You can create a module for each like function in the recipe, and then you can use the API to access each of those tasks. The module architecture is really good for validation. Since each module is self-contained, you can more easily validate each of those individual functions at a much lower level than you would in some other implementations of architecture. So, going back a slide, this functionality here, where we receive commands and provide responses, is an inherently serial operation, meaning that only one function can be run at a time. So with this in mind, if you have a function that takes longer than another function to run, then you create a blocking situation. So again, because the functionality in each of these modules can be accessed asynchronously, meaning that it can be accessed from anywhere in the application. There's no control for that. If one function is executing that takes longer than another function to execute, there may be, for example, a database call, right? Database call may be 1 minute, unfortunately, if it's a very big database call, and you may have a smaller database call that takes a less amount of time. If the larger one gets called first, then the smaller one has to wait until it finishes executing. So one way around that is to create code that can receive commands and then launch a dynamic VI. So your commands can execute simultaneously and then call back to get the result. So in general, the goal of an architecture, right, is to make it easier to perform simultaneous development. It should also make it easier to reuse the code, as well as solve some source control challenges that we'll go into shortly. The items to the right are the steps of a project lifecycle. Our project lifecycle encapsulates the life cycle of a project from start to finish. One of the first things you do is you figure out, you understand the pain of your client. So this is what your client needs from you, right? And then from there, you can gather requirements. Requirements translate client needs to technical requirements that can be used to develop code. Once you have gathered the requirements, you can generate your test scenarios. Test scenarios allow you to validate those requirements and determine whether or not those requirements have been met. This validation should be binary, pass or fail. Once you've created those test scenarios, you can generate a proposal. A proposal is an agreement between yourself and the client on what finish is and what they want. This translates the idea between both the client needs and your requirements, as well as your implementation of those requirements. From there, you enter the software development process, which contains 4 steps: developing the software, testing the software, releasing the software, and then performing feature adds or bug fixes. Within the software development project, you may do these 4 steps multiple times as you validate and ensure the functionality of different parts of your application. Once you've successfully validated all of the requirements, you can release the software to the client, and the project is complete.
So another aspect of team-based LabVIEW development is source control. Source control can be a little bit tricky in LabVIEW, but I want to back up real quick just in case someone hasn't used source control. It's a tool for tracking the revision history of your source, and also allows you to revert, branch, and merge changes as necessary. So in LabVIEW, source control is particularly difficult because unlike almost every other programming language out there, LabVIEW stores its source code as binary files. So the image on the right here shows what a VI looks like when opened up in Notepad. This makes our traditional source code tools like diff and merge no longer useful, as they rely on ASCII comparisons in order to function. So NI does provide us with LV compare and LV merge. I do want to talk about them a little bit in just a few slides here. But before I do, I want to talk about some source control methods. The first one I like to call the caveman method. This is a manual file backup, usually periodically. A lot of times when someone's implementing this, they do it at the end of the day. This is where you take a copy of all of your changes and you copy them to some folder, either on a backup drive, a network location, your choice, and give it a timestamp or some kind of revision number. I don't recommend this approach at all. Then there is centralized source control. This is like Perforce, where you have some remote repository that all of your developers are able to check in and check out code. And finally, you have decentralized source control options like Git, which allows you to not only have a remote repository, but anyone can mirror that repository and their fellow developers can check in and out of that mirror. Finally, there's also Subversion. I have to admit I'm not very proficient in Subversion. We use Git internally at Erdos Miller.
So, keeping in mind that source control is a tool that can help you manage a directory structure, a project hierarchy, while working with multiple developers. That's the function of source control when working with multiple developers, is to be able to manage all of those files, as well as share data between different developers simultaneously. So, one of the problems with LabVIEW specifically is attached to the idea that each VI is binary. LabVIEW is if you guys were not aware, LabVIEW is a compiled language, the just-in-time compiler, which means that as you modify the source code, it will recompile the VI. By default, LabVIEW stores both the compiled source and the source code in the same file. So in source control, when you modify one VI, because LabVIEW recompiles every VI that has a call to that VI, you'll see more than one change. You won't just see the change that you made, but you'll see the changes associated with the recompiled VIs as well. So one of the first things we do to make managing LabVIEW source files in source control easier is to ensure that the compiled code is separated from the source code. This ensures that when we change one file, source control sees only that change and not other changes associated with recompilations of VIs. Also, one thing we do specifically to aid the situation where you may have a merge conflict in source control, if two developers modify the same file and they attempt to commit those changes to source control, there may be a merge conflict in which you have to choose which VI should be placed into source control, right? Which version is the right version? And as John mentioned, the diff and merge tools exist, but they are harder to use, or more so, more time-consuming to use. So one way to avoid that is to be able to resolve merge conflicts, by discarding changes. So if you organize modules into folders, a developer can be quite sure that any files modified that don't belong in their folder can be discarded, which reduces the amount of merge conflicts you will have. Also, keeping in mind that you have developers developing files simultaneously and it being very time-consuming to communicate the different file names they're using, there is a strong possibility that each LabVIEW project may have file name conflicts in which two files have the exact name, such as main.vi. One way to resolve this is to either A, use file name prefixes, where we prefix each file for a certain module with a prefix, such as module A, etc. Or we use a library. A library will namespace every contained VI inside of it, ensuring that every developer, as long as their module names or the library names are unique, can name files whatever they want to. This helps both during the project and also for code reuse, in which a module may be imported into a project that has that may have an unknown set of file names.
So that brings us to the LabVIEW merge tool. Basically, everything we told you has been we've mentioned in order to aid in not having to use the merge tool. Trying to merge VIs without some kind of ASCII-based file store makes it very difficult. So this is why we talk about trying to discard changes instead of just trying to check in every change that has been made in source control, or file organization and file naming. This is why we bring up modular architectures, so that developers can be assigned to specific modules, and we can prevent them from overriding each other's changes or forcing us to merge. So the merge tool, it does not scale well at all. For example, I know this block diagram is going to be hard to see, but I have one VI that just simply increments a number in the timeout case. From that point, I branched off into two branches and made two different changes. In one branch, I added an increment case, where if the user presses a button, I increment the number. And then in another, I added a decrement case, which is the exact opposite. So when I try to merge these, the merge tool will do what it can, but at this point, it is an either-or approach. So I can either take one set of changes or another. I can't mix and match. And the merge tool is unable to take both of those event structures and merge them together. So in effect, I can choose to either include my increment case or my decrement case in my event structure. And then finally, I can go and manually add it in, but now I'm essentially duplicating efforts. So this is why we try to avoid the merge tool, because it does not scale well. And when you have large 500 VI projects, you do not want to spend a lot of time trying to merge. And the reason we end up having to merge is because in a team-based environment, we like to implement good branch methodology. Our preferred approach is Git flow. Git is in the title, but I know at least in Perforce this can be implemented without issue. So it's not specific to Git. Proper branch management makes it easy for us to revert features that have created bugs, as well as organize our release candidates and get ready for software validation. So the main principles of Git flow is that we have a few branches. The main ones are, The main ones are master and develop. So master should always have the latest functional validated release of your software, so that new developers can come in, check out that code and see some functional code, or be able to provide it to some of your testers. The development branch is where all of your development occurs. The architect is generally going to be on the development branch the majority of the time. Your architect is going to be responsible for creating the initial commits into the development branch. And from there, we branch off into several feature branches. So these can be features identified in your requirements. You can also branch all of your individual modules, which secludes all of your developers to a specific branch. When features are completed, they're merged back into the develop branch. And this is where the merge tool comes in. However, if you separate your modules, discard changes that aren't actually made, separate your compiled code from source, you should have very few merge conflicts at this point. When you are done with the development cycle and you've identified that you are ready for validation, you generate a new branch for your release candidate. At this point, all of your feature development stops. You do not merge any more features into the development branch. The whole point of the release branch is that you have added in all the features that you want at this time. So once we're on the release branch, this is when we start validating our software. We run our tests. You can make any bug fixes at this time on the release branch. And when you've identified a passing version of your software, you'll merge it back into master and give it a tag with the version number. And you'll also merge it back into development. The last branch is the hotfix branch. At times you might have released some code and a pretty bad bug was found by one of your clients. And you don't want to go back and revert all of your development and feature branches in order to get to that particular set of code to make your changes. So from there we can branch off of our master branch, implement our code, and put it back into both master and the development branch with an incremented version number. This avoids having to revert code and simplifies our source control management.
All right,
John.
so, for those project managers,
Just a question, do you use some of the governance that, for instance, GitLab can apply for you when using GitFlow?
I'm sorry, repeat that?
GitLab has a feature for using birds up to the release branch. So you can actually govern that, for instance, your architect should review the code before it goes in. Have you any experience using this?
Honestly, I think that's the first I've heard of it. I mean, I use the Git flow feature set, so I can do the commands that will handle all the branching for me and all the naming. Other than that, the only other tool I use is from GitHub. It's called LabVIEW Git ENV or Git LabVIEW ENV, which handles the integration of the LV compare and LV merge tools into Git. So that when I say Git merge, it brings up LV merge instead of its native merge tool.
GitLab is kind of a package that supports the GitFlow rather than also the governance methods that you have in GitHub.
So is that made by the Git Foundation or?
I think it's a free at least.
Okay. Write that down.
How do you, can you go back to the last slide? How do you manage conflicts when you're doing a hotfix? Do you go merge back to the development branch?
Good question. How do you manage the conflicts when you take a hotfix and merge it back into master and development? It's tough.
Same question for the feature as well.
As well as the features.
So it really depends on the nature of the hotfix, right? So if you have a nice hotfix that's just you adding a file, modifying two or three VIs, there's always the possibility that that change doesn't actually modify any code, right? Any code that's in this part of the branch or further in the branch. So ideally, you'd want to freeze the development branch after the release. But in the event that your hotfix is occurring during your development, you may be able to merge that change in. But if you can't, in that case, the hotfix it stays with this version of the application, and you may implement that hotfix again during the development phase. So you have to essentially duplicate that versus you might not be in a position to actually merge the hotfix in, especially if it's caught much after development started. It's just easier to duplicate that change and fix that bug, and then once you do the next release, that bug is a part of that release. In the feature branches, when you want to say merge either new features or you want to merge modules, ideally those features are in locations that are their own. So if it's a module, that module has its own directory, its own folder, and all of the changes associated with that feature or that module are in that one folder. So you just discard the change when you merge the two features. In the event there should be no conflicts outside of that folder, so there's less need to merge in terms of using the merge tool. Okay. Right, one more question, and we'll keep going.
What do you do when you feature a dependency for another feature? When you rebase it, so you can
So generally, you're going to have to wait until development of, because if you're dependent on one feature to be implemented, you're going to have to start your next feature after that one has been completed and merged back in. Yeah, that's about it.
Yeah, and that goes in line with multiple developers. Generally, your simultaneous development it can only work in as far as the features are independent. So if you have dependent features, generally you have to do them one after the other. All right. So before the fun part, right, before you finish a project, you have to validate your software. And you do so using requirements and test scenarios. So again, test scenarios generally allow you to have a binary output and pass-fail testing of a requirement. So if you guys remember the requirement on the screen here, a appropriate test scenario is we set the pressure to a limit physically reachable and record it here. And once it's recorded, we're going to set the pressure and then increase the pressure beyond that limit. And if the analog actually triggers, then it's a pass. If the analog doesn't trigger, it's a fail. So these types of requirements and test scenarios can be used to validate the functionality of your application. Generally, in your requirements document, there is a very long list of test scenarios that allow you to test each and every requirement in a binary sense. Some of you may be wondering, how would you test a more analog requirement? For example, a requirement to maintain a temperature set point. That's a more analog requirement. And the way to do that is one of two ways. Either you focus more in your test scenario, or you make your requirement more focused. So for example, a better requirement for any type of set point requirement would be maintain a temperature set point between the temperatures of negative 10 degrees Celsius and positive 110 degrees Celsius within 0.1 degrees Celsius. Right, so that can allow you to have a very, well, that and then a time factor, right? So I need to maintain it for at least 5 minutes, or for at least a appropriate use case will allow you to create a binary test scenario to be able to validate that requirement. So along with those test validation, you have changes. So changes occur when bugs are found, when you find that a certain implementation doesn't work as expected. And those changes will use the requirements documents, and in some cases the test scenarios, to be able to justify whether or not that those changes are in scope and out of scope, which are more appropriate for fixed-bid projects, but also very appropriate for T&M projects. When we find that a certain implementation won't work, say for example we had planned on using a CDAC, and now we have to use a CREO, the implementation is significantly different, which distills into it will cost more money. So having requirements and having test scenarios and having ways to validate whether or not your code works will allow you to better manage those changes. So once you have validated your code, you are in a position to provide a software release. As John noted earlier, software releases are generally versions of the code that are functional, have been validated, and allow you the possibility for project completion. Again, remember that the proposal defines an agreement between you and the client. So it defines the way in which you determine the project has been completed. Releases are generally provided in one of two ways. We prefer application installers if it's a software application, or if it's an API or a module that we want to reissue, so source code, we prefer using API package.
Good point. So in conclusion, we presented some strategies to mitigate this loss. You definitely want to fine-tune it to your teams. But these strategies include selecting a proper workflow, designing a good architecture that limits your coupling and increases the cohesion of your individual modules, and finally developing a known project lifecycle for handling development, deployment, as well as handling the project management and the business management side. At this time, we are co-releasing a white paper that goes into a bit more detail without being too long on this topic. You can locate this at erismiller.com/NIWeek 2016. And I'd like to open up for questions.
You guys were each using your own architectures, right? You each have your own architectures. How does that work out with your developers on learning how to actually work with the individual architect's preference on architecture?
Okay, that's a good question. So, and for anyone who didn't hear, you said Antonio and I both use two different architectures, and the question is, how do we handle training the developers and working with developers when they need to learn two different architectures, and how the developers deal with us? So we try to keep our architectures very simple. I know that both Antonio and I have project templates already laid out for our particular architecture, so we can create new projects from it, complete with your bookmarks and your to-dos. But generally, it ends up just being a training issue, explaining to developers what they can modify and what they can't. And then on, say, the source control side, we end up setting up the ignore settings, so preventing them from being able to push and pull code into the source from folders that don't belong to their particular defined roles. Does that help at all?
Yeah. A follow-up question: why don't you standardize on one architecture?
Generally, we like the idea that your implementation, your architecture should follow what makes you most comfortable. So for an architect, there's always the fear or the issue that if you implement someone else's architecture, your development may not be as correct, you may not be as efficient because you have to learn someone else's architecture. So generally, the idea is that we develop architecture that make us most comfortable, and for developers, it's really good that there's always a possibility that learning or standardizing on one architecture will cripple them in the sense that if they have to pick up somebody else's code or come into a project for the first time that they've never seen before that somebody else developed, they may expect that this architecture should be like my architecture, and it's not. It's very different, and I don't know how to fix the problem. So we get the blank BI syndrome in a way with opening up new projects. And we always want to try to transfer that savings in terms of working on an architecture that's most efficient for you to the customer.
And also, there's a bit of a training component to it as well. We work in team-based projects a lot, but we're also a relatively small LabVIEW team compared to some of the alliance partners that are here. And so we're generally trying to expose some of the developers and CLADs to newer ideas and newer architectures. So standardizing on one doesn't give them a good range of capabilities of LabVIEW. If we were a much larger team, it would probably be more beneficial to standardize. Just for managing, say, 10, 20 developers, I imagine would be a lot more difficult than, say, a team of 5.
Will these slides be available?
These slides, yes, they're available at the same link as well.
Yeah, and they're also are available on the app. There should be a PDF.
Quick comments. One is that code embedding separation is great, but you should know that it doesn't play nicely with Express CI. The other one is that last time I checked, which was 2015, merging is okay, but it doesn't work for classes, libraries, or projects. Maybe it's fixed by now. And then lastly, your point on not using merging, is there a reason why you just don't force locks in your source control?
Right. So so we try to because sometimes it's a lot of admin overhead. So we can lock it out and say that, hey, you can only merge here. But for a lot of projects, that's a lot of overhead. So it's much easier in a smaller company to say, hey, don't push this change with these coders because we don't matter for your.
If you're going to do that, why not force all the developers to lock a file before they modify?
It's more convention, so it's not something that we do.
What about code reuse? How do you handle these libraries that are being
So our preferred approach is to use the VI Package Manager. If you have VIPM Pro, it does support managing its own repository. And we like to store that repository on something like Dropbox, some shared cloud service. And so all of us can then register for that repository. And anytime someone releases a new BIPM, we all get updates. So that's our preferred approach to module reuse and code sharing.
What do you guys use for like a code review strategy? Does it depend on team size and how frequently do you generally do it?
We tend to fine tune to the project. So if we're working on, say, an agile type quick change, you'll generally want to do it before once a week. For some of our like long-term projects where we are trying to design and implement, your waterfall approach, trying to get all the project done in one go. It's definitely going to be a little more often, usually around big changes and especially around code merges in source. You'll want to do a code review before any kind of big merge.
Do you do an architectural review between the two of you when you start a project?
Not as often anymore because I'm very familiar with Intodio's architecture. I've seen it several times. But if we were to bring up any new architecture, definitely an architectural review. But also we usually discuss project requirements and determine which architectures might be better prior to even beginning to architect.
What is your largest project that you implement in terms of the numbers of PIs using the settings of the separated source from the combined code from the source?
So I think the 300 or so VIs. It's kind of like the number is kind of arbitrary. Like so again,
How many?
about 300 VIs.
300.
Yeah, about 300 individual VIs.
Okay.
Yeah, I mean it's like what's is there like a specific thing you're interested in or just in general?
Yeah, because I'm working on a very large project. So like
Yeah.
2,000, yeah, it's more than
So like you said earlier.
So I was happy to hear your experience of using this.
Yeah, and so to add to it in general, like he gave some examples of where they could cause problems, like express VIs. It also causes problems if you're doing dynamic, like you're opening VI dynamically. So like there's a couple of caveats that NI has on their website about using it. So just be aware that there are a couple of functions that don't work as well to separate the code. But otherwise, it should be any really big functional issues.
And
You're close somewhere to this architecture.
We're not yet, but it's on the plan. So we plan to release it as a blog post, but we don't have it yet.
Okay, so you said that each module is using unique DVR values, right? So why you're using shift registers?
Right. So two different architectures. So for the MVVM, he uses DVRs to store the information, and for me, I use modules. So it's a QMH. So it's stored. The private data, for example, will be stored in the shift register. So two separate architectures.
I just want to point out real quick with the separation of compiled code for your plugin architectures and the instances where that doesn't work. There is the option to create a source distribution and compile a source distribution, use that for your plugins. That forces LabVIEW to compile the code and store it in the same VI so that the runtime engine can execute it.
I like your MVVM framework. It seems very simple. How does it compare with
Are you referring to Delacore's? I've never actually used Delacore's QMH, so I can't totally comment on it. This is more of an event-based, so the idea is in a perfect world you would never be polling for any information. Everything would just be purely a cause and effect or demand and response operation. That doesn't always work out, especially when you're doing data acquisition. You're going to need some periodic polling of the DAC hardware. Or your serial FPGA hardware.
You said you would post some information on how you implemented MVVM?
We have some future blog updates in which I will be going into extreme detail on MVVM, but I don't have any detailed info yet. It is my goal to eventually release it onto the LabVIEW Tools network as a project template.
We got about 1 minute left.
You said you use VI Package Manager for external code reuse, right?
Yes.
So if you have a legacy project come back and it's using older versions of your VI package manager, how do you handle that situation?
So one of the solutions, right, is that for sure we have access to those old packages, right? So we can load those. We can say let's install an older version of the VI package to support this legacy legacy software. So that's one solution.
How would you remember what versions you're using? Is it like a README or something?
So I know one of the things that we do now for sure, this is more of a hindsight issue, but we do create a dependency package using the VI package manager that pretty much creates one file that has all the dependencies for a certain project. So in the event we're not sure which one we did install, we do have that installed.
And that's in your repo?
Yeah. So we have a dependency folder with that. Again, with the older projects, best case scenario, right, is that we have an idea of which one we installed. Hopefully, when you look at the source code, we can pull one of the older versions, something like that. But otherwise, it's just, let's just keep testing until we find a version that works.
I think we're out of time, so I'm going to let out, but I'm happy to answer questions. I'll stick around as long as NI will let me.